Hi everybody, my name is Dr. Michael Stewart. I'm from the University of Western Australia, and today I'd like to talk about automating technical text classification using artificial intelligence and natural language processing. So unstructured text is absolutely everywhere, and approximately 70% of all data in organizations is unstructured. But manually classifying these unstructured texts to sort of extract useful information out of them is something that takes significant time and effort. And manual work like this is also prone to human error because everyone has their own unique view of the world. You think of a single sentence, two people might actually read it and get sort of different meanings out of it. And these issues mean that unstructured text is seriously underutilized, even though it captures really valuable business information. And I'll show you an example of that on this slide. So this is a sort of a screenshot from a tool that we've built called Echidna. And the goal of Echidna is to kind of use a natural language processing pipeline to extract information out of maintenance work orders, which are on the left, and visualize it so that subject matter experts, for example, reliability engineers, can get a good understanding of their data. So on the left-hand side here, we have some maintenance work orders. So these capture information about the work that was done on an asset and what's gone wrong, etc. So things like fixed leak on pump broken, need repair. You can sort of see that this technical language here contains a lot of really valuable information, like what went wrong, what has been done to fix it, and so on. So we've basically fed this into a pipeline and then produced this graph using that pipeline and kind of visualized it in a way that's really easy to understand from a subject matter expert's point of view. So on the right-hand side, you can see we've got a few different colors of what we call nodes in a graph. So the greens represent items in these work orders, the reds represent observations, and the blues represent activities. So for example, here, somebody has clicked on the pump node, and they're looking at all the different relationships around that. So they can get this really quick understanding that, okay, a pump has had 8 leaks, it's been repaired once, been replaced once, and so on. And all of this is kind of captured in this text and been automatically classified using AI and natural language processing. And you've also got kind of tools for filtering and looking at different assets. The whole goal of this is essentially to take what's in the text and make it extremely transparent and easy to understand for a domain expert. And all of this is made possible using natural language processing. And feel free to check out the demo at the link below. So now I'd like to talk about a typical pipeline, an AI or a natural language processing pipeline that can be used to do something like this, or really any kind of classification task. And you can kind of see I've color coded them here. So we've got data modeling, annotation, model training, fine tuning, and inference. And the blue boxes represent tasks that are typically going to be performed by data scientists or data engineers. And the orange ones are subject matter experts. So the very first step here is data modeling. This is where data scientists and subject matter experts will come together and identify what kind of information they want to actually capture in the text. So in the example before with Echidna, we might decide we need to capture items, we need to capture activities, and we need to capture observations. And there could be some other things in there as well, like locations and things like that. And that is a step that really needs to be done by both the data scientists and the subject matter experts. It's really key that there's collaboration here because data scientists understand the model and they understand what works and what doesn't and what can actually feasibly be captured and so on. The subject matter experts understand the data and what they actually need to get out of it. So this is something where there's sort of discussions and collaboration and so on. And once a model or a hierarchy of entity types, for example, have been discussed and agreed upon, it's time to start annotating. And this is the second box here, annotation. This is where subject matter experts go through a set of training data, for example, say like 1,000 or so, or less or more, depending on the task, and they label it basically. So they're essentially telling the computer what to do, teaching the computer how it should understand this text. And I'll show an example of an annotation tool in the next slide as well, so you can kind of get an idea of what annotation looks like. The next step is for the data scientists to go and train the model or fine tune depending on the model itself. And the goal of this is to kind of get a model that can do this task pretty well, based on training it on the annotated data. And finally, the last step is model inference. This is where you take the trained model and you apply it to what we call unseen data, basically. Data that the model hasn't seen before. This could be potentially hundreds of thousands of records that weren't in the training set. And you run the model over those, and you essentially get the model to do what the subject matter experts were doing, but automatically, very quickly, and at scale. And this is one of those other tasks that also needs to be done collaboratively. So data scientists will run the inference and work with the model. Subject matter experts will need to be there to interpret the results, see whether they worked or whether the model was successful or not. Potentially also feedback into the data modeling if they realize there's some information in there that hasn't been captured, or those sorts of things that requires a kind of understanding of the data. And once this is sort of working to some sufficient level of performance, you can go ahead and do some kind of business task. For example, building a graph, like with the case of echidna, or doing some classification, and so on. So I mentioned annotation previously in the slide before this one. And now I'd like to just kind of introduce the idea of an annotation tool. So nowadays, annotation is super easy because we have a lot of sort of cutting edge annotation tools available. And the one that I'd like to just kind of show here on the right is a tool called QuickGraph. So this was built by one of our PhD students, Tyler Bacorn, and it's already been used to kind of annotate technical text by several global companies. So the interface on the right here is very straightforward. Kind of get an idea of what annotation looks like. So the subject matter expert will come in and essentially highlight these words individually or together and give them a label. So tighten might be an activity, loose might be a realizable entity, and so on. Essentially what they're doing is teaching the model how to understand these texts. And annotated data, just one of the points I'd like to make in this presentation. So annotated data is extremely valuable when it's produced by subject matter experts. If you can get really good quality annotated data, you can use that to train any model. Even as new models come out, which they do, like every day, there's some model that has slightly better performance. As long as you have a set of annotated data, you can quickly retrain a model. That's never going to change. So no matter which models come out, you can always just retrain it with an annotated data set. And as a result, it's extremely valuable to have that annotated data available. And some people think sort of, why do we need annotated data? We've got ChatGPT. I guess a point I'd like to make is that GPT only works well because it's been trained on a huge amount of annotated data, like millions of sentences that have been kind of arranged into question answer pairs. And that kind of goes to show like annotated data is still really important. And that's why ChatGPT works so well. Now, I'd like to kind of talk about a case study, I guess. And this is a task called failure mode classification. And this is kind of some work that we've done looking at the applicability of using large language models to perform one of these classification tasks. So failure mode classification is a task that's performed by reliability engineers. And what it does is it captures and codes failures and other undesirable events. And these codes are then used to prioritize improvement work and update maintenance strategies. So it's a really critical task. It's very important. But as one of these tasks, like I've mentioned before, it's very difficult to do manually, as observations that have been written down by field technicians, everybody interprets them slightly differently. And it's very different. It's difficult for two people to agree on the exact same, failure mode code for the same sentence. Everyone's got their own sort of unique view of the world. So here's an example of what failure mode classification looks like. So on the left-hand side, we've got work orders. So fixed leak on pump, pump broken, need repair, and so on, as we saw with the echidna. And on the right-hand side, we've got a failure mode code, leak, breakdown, and so on. And this could be potentially repeated for hundreds of thousands of work orders. So it's not something that's easy or cheap to do manually. It's an incredibly laborious process trying to understand each of these. And as a result, this is something that's really good to automate. If you can do this at scale, it's incredibly valuable. And that's why we sort of look at the AI and the NLP to do this task. So large language models, I'm sure many or all of you have already sort of grown familiar with them over the past year or two as they've gained a lot of popularity. They typically exhibit extremely good performance on a wide range of tasks, really anything involving natural language, writing code, generating, emails, whatever, anything NLP, they're really good. And we were kind of interested in trying to figure out, do they work well on technical language? For example, work orders. And that was really the goal of this case study. We wanted to see, do LLMs work well on failure mode classification, for example? And all of this work that I'm going to be discussing is available in this paper at the bottom. So feel free to check it out. So before I kind of launch into the case study a little bit, I just like to talk about how LLMs differ from sort of traditional language models. So typically large language models, they're used off the shelf. So we don't actually need to train them. So for example, you interact with ChatGPT through a web browser or something, you'll ask it to do something. You don't actually have to train it to do it, right? It's just kind of, it already knows how to do it, sort of thing. It's off the shelf, no training required. But they can also be fed prompts to alter their output. This is what we call prompt engineering. This is when you give prompt, it gives you an answer, but it's not quite right. You kind of iteratively edit the prompt. You say, okay, could you please not put this part in there? I need you to add this bit, etc. There's a lot of different forms of prompt engineering, but essentially it's trying to get the model to produce what you want in the output. But similarly to the traditional language models, they can also be fine-tuned. Typically, this is done through sort of APIs. And I'll kind of show an example of this because we did actually fine-tune GPT. So they can be fine-tuned. Some people don't do it, but it is an important point to note here. So the first thing we'd like to try in this, or we wanted to try in this particular case study, was what happens if we just take an LLM off the shelf? So in this case, we use GPT 3.5, and we just asked GPT 3.5 to classify the failure mode of the following observation, and then we gave it the observation. So it runs for a while on trip, for example. And this is what it came up with. So for that particular one, it just gives you this incredibly long-winded explanation of what it is. And it's going on about, oh, it's not really sure and everything like that. You can say it's an interesting response, but it's not something you could actually use for any kind of analysis. And this is because GPT is essentially an assistant. It's designed to output things that are as if you're talking to a person. So that's understandable as to why it actually produced it like this. But ultimately, just doing it this way is not useful for analysis. You're not going to be processing hundreds of thousands of these. It's just too noisy, basically, to do any form of further work with. So what we next tried was to edit the prompt, do some prompt engineering. And we basically put in a bit extra onto the prompt saying your answer should only contain the failure mode and nothing else. And now we can start to see it's getting a bit better. It's starting to produce very short and concise responses, which is what we want. Although some of them aren't correct. So for example, runs for a while on trip is not overheating, but that's fair enough. You can start to see some big issues as you look further down. So for the first one, so if you look at NA and no failure mode can be determined, those essentially mean the same thing. So they're not consistent. The responses aren't consistent in any way. It comes up with many different ways of saying the same thing, which is not ideal for analysis later on. Things like stiff operation and noisy operation as well. You kind of get the sense that it's just making up its own failure mode codes. They're not from any kind of engineering sort of knowledge base or anything like that. They're just almost hallucinated labels that it's just kind of put together. And if you were to run this over potentially like 1,000 work orders, you would end up getting hundreds of different failure modes. So ultimately, this is not really useful either, unfortunately. So then we thought, okay, why don't we just get it to produce a list, produce a failure mode from a list that we know contains a set of structured failure mode codes. So we edited the prompt again to just say your response must be one of the failure modes from this list. And we gave it a list of, I think, 22 different failure mode codes from the ISO 14224. And we found that this does improve performance substantially. Like it starts to get pretty good. It starts to produce labels from that list. However, it still kind of hallucinated quite a few. It started to make up its own labels based on labels from the ISO. So still a bit better, but not great. Still issues with consistency. And ultimately, what we realized here was that LLMs are not readily usable on technical texts without doing some kind of fine tuning. And this requires human annotated data. Once again, highlighting the importance of annotated data. And here are the results. So narrow AI was a model that we looked at sort of a year before this GPT LLM stuff on this failure mode code task. And we trained this model on 500 failure mode observation failure mode code pairs that we labeled. And we call it narrow AI because it's basically an AI model that's trained to do that one task and nothing else. And you can see the micro F1 score is about 0.6. That's sort of our baseline. Now, GPT 3.5 off the shelf was actually substantially worse than that. Right, so without the annotated data, it was not great. It was okay on some things, but for the most part, it was not as good as the model that was only trained on the 500. Yeah, it didn't have all the entire internet in its training. It was just that 500 record data set. But the interesting part here is that GPT 3.5, once fine-tuned on that same data set of 500, ended up being substantially better than the narrow AI. And what this really highlights is that the annotated data is incredibly valuable and important. The GPT by itself, not great, but with the fine-tuned annotated data set, it does substantially better, which we found really interesting. So just some quick notes on large language models. Most companies probably want to use offline large language models, just from a data provenance perspective. But there are, fortunately, other options like Llama and ChatGLM that are offline, as opposed to GPT, which is online. And like I showed in the previous slide, LLMs can be fine-tuned to exhibit excellent performance, but unfortunately, their results are inconsistent. So we actually ran these same experiments a year later, and the results were completely different. And we don't know why. We suspect GPT may have changed their training process or something, but ultimately we never found out like what actually happened. So from a production point of view, that's not great. Like LLMs, online ones at least, are still a bit of a black box, and they can be very inconsistent. So using them in a production setting, you really have to be aware of that. And these results, of course, are for GPT 3.5, and results can change with new model releases. And one of the key takeaways we found was that narrow AI, like the model I showed in the previous slide, it's still incredibly useful. It may not get as good performance as the sort of best case with GPT, but the results are reproducible. You can get the same results every time, which is really valuable. So in conclusion, we've looked at a typical pipeline for utilizing artificial intelligence and natural language processing to classify technical text automatically. And two of the key takeaways I'd like to present here are, number one is collaboration between data scientists and engineers is incredibly important. So data scientists understand the models, SMEs understand the data. The key to success here is collaboration between those two. And ultimately, models are only as good as the data that they're trained on. And annotated data, really, annotated data produced by the subject matter experts is key to good performance in technical domains. So thanks so much. I've included a link to the UWA Natural and Technical Language Processing group there as well. Feel free to check it out. Thanks so much.